Hi, everyone. So there were a lot of great discussions and presentations over the past 2 days, and I'm sort of very happy to be, I wouldn't say the last one, because there will be plenty of discussions after that, but I think it's quite an interesting topic for concluding this day. You've seen different libraries that were presented with their roadmaps, updates, new approaches. You've seen a lot of talks about AI and machine learning. You've heard the different keynotes talking about sort of like visions and where things are going. At Enthought, it's been, as my colleague Mark was saying, like about 17, 18 years that we're deploying scientific applications. And so there are quite a lot of challenges related to that. And I basically wanted to spend some time today to talk about sort of those challenges and how we've solved them. So that's the goal of the discussion today. Yeah, I'll just like skip the introduction. So first, some words about the scientific code and what it means to like write scientific code. So most of the time, scientific code is not written by computer scientists. It's basically written by scientists, analysts, engineers. So people that have not as their primary mission day to day to write code. Typically, they write code because they have to write code, not because they want to write code. And so that means they focused on one given thing, which is solving the scientific problem. They're going to focus on, I don't know, getting the right results for the modeling of a given set of equations, or potentially improving how fast their modeling is doing, or simulations are basically running day to day because it takes too much time. They're not really interested about, most of the time, about the architectures, about clean code, about the fact that somebody else is going to read the code, maybe. Yesterday, one of the gentlemen was talking about his company where they typically don't work together, they work like individually. So when you work individually, you have different kind of standards for the code you write. So the iterations that around the code basically are mostly focused on the scientific aspect. So that's one first point. The second point is that typically you want to like write as few code as possible. You just want to like look at the domain that you're trying to solve, focus on that, find the equations you need to implement. Ideally, delegate most of the work to external libraries. So if people have implemented some nice, I don't know, FFTs, you want to reuse those ones and not write your own. At least today, that would be very interesting if you do that. And so they heavily depend on existing libraries, but they also heavily depend on examples. And we've been so lucky in the past, I don't know, 8, 10 years to see many libraries out there like spending a lot of time on good libraries of examples. If you look at Matplotlib has like a really extensive and nice set of examples. You can just go over there, look at the outputs of what Matplotlib does. So it's a 2D visualization library for those of you that don't know about it. And you can, for each of the examples, find the code, use the code, change the code, and then integrate that potentially in your day-to-day work. Can I come back? Yep. It's back. So the scientific code typically depends on examples that you can find on the internet or like with your colleagues and existing libraries. And finally, like one of the typical aspects of scientific code is that the person writing that code has not much time to take care of like about the gory internal details of the underlying layers, the things that are like behind the scientific code they write. And so if you think about the problems of like user interfaces, about let's say NumPy that uses a BLAST LabPack implementation, and so like what it means to have to use one or the other. So typically you don't really care about those things. You want to benefit from something that's great, that has been developed over the past 30 years plus in some case, and it should just work. So you're looking at your computer, at least you would want to look at your computer as an ally and not as an enemy. I think facts show that most of the time, for many of us, it's basically a pain point. Like that computer doesn't do what it should be doing, and so you're getting, let's say, a Jupyter Notebook. That would be a typical fact. You would get a Jupyter Notebook by email from one of your colleagues. You execute that, and it doesn't work, and then you start like an interesting journey trying to solve that problem. So that's what happens typically with scientific code. It doesn't mean that it happens all the time, but that's a typical problem. The second thing that happens with scientific code is how we're sharing it. So you see that I have 3 different bullet points there, and so there's sort of different levels of sophistications. The first type of sharing is by email or USB sticks, or like even better, like network drives. I don't know how many of you use that as like a way for sharing scientific code. So I'm going to raise my hand, like nobody's going to kill me in my company, please. So it happens. So I'm sharing the Jupyter notebooks by email every now and then. I'm sharing Python scripts every now and then with emails too. It's definitely not great practice, but that's how it's done. Why is it done like that? How do people share Excel files? Most of the time by emails. Sometimes they use SharePoint, but like not many people do that. They're basically using most of the time emails. So it's just like part of the standard practice. Slightly better, so you can use version control. And so if you like lucky enough to know how that works, you can use GitHub, GitLab, Bitbucket, like an internal version control system, and use that for sharing code with yourself or with your colleagues potentially. Now, I'm talking about scientific code and scientists and engineers, and so even if, especially in the SciPy community, this is very standard practice to use version control, it's not standard practice in science in general. And if you're not sure about that, I think, there's so many places all over the world where you can find like companies that don't use version control. So it's not bad. Like things are evolving, and so it's definitely getting more standard, but it's not yet fully standard. And finally, you could think about sharing your code as a Python package through PyPy or having a local server or things like that. Sharing your code as Python package has like another set of challenges because you need to like create the package, feed the package with the content, and there's the way you're structuring your code, the documentation related to that, and so on and on and on. It's much more involved. And as I was saying in bullet number 3 over there, so you don't have much time. You basically prefer focusing on the science than building a package. So that's sort of the first aspects of the scientific code. The second one is that, so you're depending on a lot of libraries. I tend to call that the SciPy stack. And so the SciPy stack is something much wider than just the SciPy package. It's basically the fact that you're using the Python ecosystem, SciPy obviously, but SciPy depends on NumPy. And then you might be using Jupyter, you might be using the IPython REPL, you might be using machine learning libraries, you might be using visualization libraries, storage libraries like HDF5 or others, and so on and on and on. So typically the number of dependencies there, or number of packages that you're using is very large. Mark, in a talk earlier today, was talking about one of our applications where we have 160 different packages for an application. And so like think about the dependencies between all those packages. So if you pick scikit-learn, you probably want to make sure that you have the right NumPy version. And if NumPy depends on the MKL and scikit-learn also, you need to make sure that they basically align so that they had, anyway, like it's getting very complex. And back to slide number 1. So you don't want to spend time working on that. This is just like time lost because you prefer focusing on the science. So this is the context. So within that context, so like there is this question of reproducibility, and it can mean many, many different things. In this talk, I'm basically focusing on a very simple use case. I spent a little bit of time on the internet. I went to the Matplotlib website, and I downloaded an example. So this is the streamplot demo example. Just cut and paste. And I want to basically make that, I want to execute it so that I can see the streamplot on my machine. I'm interested in using that for analyzing some results of my simulation work. Now, I'm not the only one interested in that, so my colleagues in the lab are also interested in that. So how do I make sure that I can execute this code in a reliable way, and after that, share that with my colleague down the hall, and so that he can basically execute my modified version of this example, and so that he can see the stream plot out of, let's say, a given data set. So I download the file, and I start looking at it, and in first interesting set of information, I see my import line. And so import NumPy as NP, and then import matplotlib pyplot as PLT. Great. So how do I know what I need to execute that code. I need NumPy and Matplotlib. That's good information, but that's far from being enough. I have no information about the library versions. Which version of NumPy is that? Which version of Matplotlib? Is it Matplotlib 2, Matplotlib 3? Is it NumPy latest one? Is it NumPy 1, I don't know, 13, whatever? On top of that, so some of those libraries have like dependencies behind them. For example, like NumPy can be compiled against the math kernel library from Intel, or can be compiled against OpenBLAS or whatever. So I don't know which one was used. It's a visualization code, so it's not very important, but if I was doing some computation there, so it might be very important. Second thing, there might be like some backend that are connected to that. So Matplotlib needs to visualize or display like a plot. And so it needs a user interface backend. What type of user interface backend do I use? I can use TK, Qt, WX, Qt4, Qt5. I don't know. At least I can't guess from that code. If you can guess from that code, you're great, but it's very hard for like others. So we don't know which library versions. We don't know which dependencies behind, so like dependencies of those libraries. And finally, we don't even know which Python version. So reading that code, so you don't know if it's Python 2 or Python 3. You might guess that from the syntax, but even in this code, it might be not trivial. So we're basically lacking the execution context. We have no way of knowing how to make that work. So that's a starting point. Just to make it to work on top of that, so Jupyter notebooks are really common nowadays. There is like this great GitHub repo where you have a list of a lot of Jupyter notebook examples. So I decided to go over there and find like an example of using OpenCV. So this is a Jupyter notebook. You have the link down there, and that one just shows you how you can do work with features in computer vision using OpenCV. Same problem. You have the dependencies, import CV2. No clue which OpenCV version is that. They basically added some nice comments over there, but like nothing about the version. So that's one key problem with Python in general, is that you don't have the version information within the code there, and typically people don't spend the time to add that over there. One thing which I think is another issue for scientists using Jupyter notebooks is the fact that the Jupyter frontend is a browser. So you're using Chrome, Firefox, whatever other browser you can think about. And so that's your interface with the Python code. The thing is that, as was highlighted yesterday in the Jupyter Internet Gateway presentation, the execution of the code happens in a separate process with the Python kernel. And so when something doesn't work in the web interface, now you have to get to your terminal, interact with the terminal, know which Python environment you have to manage and change. So it's basically make things way harder. So second important point. So the two key challenges here for us are like getting more information about the execution environment. So how do we get the right Python environment? How do we make sure that we have the right environment? And how do we make sure that we can reproduce that environment at some other place? And second, so getting the environment is good, but like also all the dependencies related to that. That's just a large pain point. So I've just shown here a Python script and then a Jupyter notebook. Things get even harder when you're thinking about applications. And we have a great example. So I don't know how many of you know MyAVI. MyAVI is a Python application built on top of the Enthought tool suite. And it's basically very, very nice for analyzing and visualizing 3D data sets. So it's built on top of VTK, which is a C++ library, which allows us to do the rendering and the analysis and the pipeline of code around that, the 3D data set that you're looking at. The problem with that is that MyAVI is great, but it basically evolved through time with the versions of VTK. And so VTK has version 6, 7, and 8 that are sort of the latest ones. So the MyAVI code basically allows you to choose VTK 6, 7, or 8. So which one do you pick? You don't know. You definitely don't know from the code. And if you want to run the application, so getting the right VTK version might be tricky because compiling VTK is not that easy. And second thing, MyAVI also allows you to have multiple user interface backend. So WX Python, Qt, Qt4, Qt5, and others. So if you go to Stack Overflow and you type MyAVI, you're going to find about, I think, 600 questions or something like that. a number of them are just about the fact that if you do pip install MyAVI, it never works. It never works because the dependencies behind MyAVI can't be resolved easily, because it's not easy to get the VTK version, because it's not easy to choose the UI backend. So like with Qt, for example, like you have the choice between PyQt4, PyQt5, you have PySide, PySide2, like all those things are basically like not easy to handle. So when you get an application, it's even worse, because now when you want to ship an easy application to your, let's say, your customer or the end user that just wants to install MyAVI and click on a button so that it pops up and he can load the data, then it becomes a dependency nightmare and an installation nightmare, and then you're losing users because they just can't use the tool. So figuring out deployment is like really a key for, first of all, removing nightmares from your end users, and in particular scientists. Remember that they don't want to spend time in the gory details behind the application or the code. They just want to get that little example application to run, or extend it, or improve it, or create their own script. So it's really, really important. And second thing, once you have solved the deployment question, you basically increase the potential for your application to be reused and adopted. And honestly, for MyAVI, if we had done a lot of the things we have done in the past years sooner, we would have way more users. That application would have like much more adoption. So obviously, like Enthought is not the only one that have looked at that. There are plenty of solutions out there. And so some of them are really complex, some others are pretty simple. They have different levels of sophistication and level of success. So you can use requirements file if you're just using pip, for example. That gives you like a first type of solution. I'm not going to discuss the details of those solutions because I don't have the time for that. There is piphams, there is binder for Jupyter, there is et cetera, et cetera. At Enthought, so we built our own stack for like 10 years plus. So we basically solved that with a given tool. And that tool is called the Enthought Deployment Manager. And I think it's important basically for you to be aware of that. So it's available out on the internet as under a BSD license, so anybody can download it. The source code is available under a BSD license and will be available on SciPy very soon. There is just a conflict of naming with another package that also called EDM that we need to solve. And there is an extensive documentation that's available on the docs.enthought.com. I'm not going to discuss the full details of what EDM can do, but just focus on the reproducibility questions with a simple use case. And we can have discussions after the talk about EDM if you're interested. So, as I said, a very simple use case. We're taking the matplotlib example, the stream plot. And the only thing we want to do is being able to create an environment, execute that code, and then sharing this environment with somebody else. That's the sort of our homework for today, or not homework, I'm going to do that in front of you. So what do we have to do? First of all, we need to create a Python environment to ensure that we can make sure that the script runs, the one that we downloaded, and we can potentially improve it. I'm not going to do the improvable parts, but just making sure it works. And after that, we need to find a way to make sure that somebody else can create the same kind of environment on a different computer. So what are the steps? And so I've just summarized the steps here, and I'm going to show you the code just after that. So first step, create a Python environment. Second step, populate the environment with the appropriate packages. Third step, you can use the script that you downloaded, or build your application, or generate a new notebook, or whatever. After that, you're in a position to export, basically, from that Python environment, you can export what we call a bundle file. And so this bundle file is the key of this talk, basically. And that bundle file will be, you'll be able to provide that to someone else. Someone else is going to be able to take that, create exactly the same environment, and execute the code over there. So those are the steps. How does that look like? So first, pale face on the scientist's visage. This is a terminal. So you have to use the terminal for like interacting with DDM by default. You can obviously have some graphical user interface on top of that, but most of the time, so those tools are terminal-based. So the first step is creating an environment. And so as you see on the first line there, I'm just calling the EDM executable, EDM environment, create, version 3.6. I'm asking a Python 3.6 environment, and I'm giving it a name, SciPy Japan Development. It's going to connect to the internet, fetch the Python runtime, install that locally, add some default packages, and then you're up and running. Now you have a Python 3.6 environment installed. Second step, populating the packages. So I need matplotlib, and I need a user interface backend. So I'm asking for installing matplotlib 224 and PyQt in this specific case. And I do that within my SciPy Japan development environment. Very basic. One important thing that you see there, I've just removed like a lot of the verbose output there, but the fact that I install matplotlib, basically it installs NumPy, which also installs the MKL. So EDM is responsible for managing basically the dependencies between the packages. And it makes sure that the packages you install are working. If you want to compare EDM to something out there, you can compare EDM to like what the Debian stable environment does. So it basically ensures that you always have a working set of packages. And so once I have executed the second step, so matplotlib has been installed, the other packages have also been installed. And so I can now execute my streamplot example, and I'm very happy. I start connecting that to my research environment. I can load the data from my last simulation and admire basically the stream plots out of that simulation. Very happy. So now I want to share that code and the environment that comes with it with my buddy down the hall. And so what do I have to do? EDM provides that export function. So EDM environment, please export my SciPy Japan deployment environment, and I give it a file name. So you see that SciPy Japan deployment.bundle. That extension is not very important. It's just so that you can recognize a bundle file. And there is a metadata format, so I'm just using the 2.0. You can ignore that. It's just by default. And now I have this bundle file, which is a JSON file. We can look at that in a minute. And it's supposed to give me all what I need to reproduce exactly that environment on some other place. So what is inside of the bundle file? How can I make sure that it's reproducing exactly the same environment in another computer? So three very important things. The first one is the list of repositories that are basically required to install the packages and the runtime for the environment. So it basically means that we're picking those packages and the Python runtimes from another place, somewhere. So we need to know where it comes from. The second thing is the exhaustive list of requirements. So I need to know exactly which version of matplotlib, which version of NumPy, which version of the MKL, which version of PyQt, and so on and on. And it must be exhaustive. You can't basically lack any of the existing dependencies, and the versions needs to be pretty explicit. So if we look inside of the JSON file, so you see that on the right here, I've just extracted some specific information out of that. So the second part, the requirements part, you see that for matplotlib, the requirement is I need the package called matplotlib. It needs to come from the Enthought free repo. It has a version which is 2.2.4.1, and important information, we have this SHA-256. What is that? That's basically a checksum that's computed when we basically make the package available on the server side, and that's basically verified when you get the package locally. So it ensures that version 2.2.4.1 is basically the right one, and that you're not installing a different version that somebody else would have changed without increasing the build number or whatever. Third information that's in the bundle file, it's the Python runtime information. So it's Python 3.6. It's not any type of Python 3.6. It's Python 3.6.5, which is +2, which is like a second build that we did. It's for Red Hat 6. It basically comes from the Enthought 3. We also have a checksum there and like some other information. So based on that now, I can take that bundle file and give it back to an EDM installation and say, hey, please recreate exactly the same environment, and I should be in a position to execute my code the very same way. So how do I do that? EDM environment import, you give it the file, you give a name to your target environment. I call that imported environment, which is not a great name, and then I can use the environment to execute that code again. Simple and easy. So now you can do basically one more step there. If you have a bundle which allows you to create a Python environment in a reproducible way, if you add to the bundle notion some notions of entry points, so something you can execute in the Python environment, then you have the notion of an application. And so that's basically where we pushed EDM now. EDM has this notion of application, which is just a bundle file with entry points. And so at the bottom here, we have an example that we put in EDM, in the EDM repositories for MyAVI. That MyAVI crazy problems of dependency that we've seen in the past is completely solved with this. If you ask for installing the MyAVI application, it basically comes with all the right dependencies. No more, you don't need to choose VTK anymore. You don't need to choose if it's PyQt or PySide. You just ask, I want MyAVI, install MyAVI please, and start MyAVI. That's how simple as it should be. And that's basically like, yeah, no more nightmares, and just like enjoying some tools. And here on the right, you basically see the graphical user interface that basically does exactly the same thing. So I'm now just concluding the talk there by saying, so through a very minimal use case, so we simplified that to sort of the strict minimum. I have to, yeah, have 1 more minute? Yeah. Great. So using EDM, so the Enthought Deployment Manager, so we have some sort of a very robust solution for deploying the application that are deployed at Enthought every day. That tool is available under a BSD license on the internet, so everyone can use that. And so anybody can basically benefit from those features. A lot more can be done around the workflow that I've seen here. So you can do like advanced dependency resolution. I haven't talked about data bundles. So the bundle file, which is JSON file, can also contain the packages and the runtime. So you can now have something that you can reuse completely offline. You can have bundle generation on multiple platforms. So if you're on Linux, you can generate a bundle for Windows, for example. That's quite handy. Enthought's using that every day for our continuous integration systems. And finally, like bundles can basically be used server-side if needed. So that said, I'm very happy to take questions. There are like a lot more discussions potentially about EDM that we can take after this talk if you want. But so if you have any questions on this workflow, I'm very happy to answer those ones.
Thank you, Didrik. That's very good. Any questions from the audience?
I'm wondering about multi-platform support because I saw the Red Hat marker there. And so if you want to share that environment with someone who has a Mac, is there a way to say, make this OS independent?
So two different ways. So either you generate the bundle on a given platform, and so you have the bundle for that platform, or you have an EDM bundle, generate bundle, which allows you to generate a bundle for a target platform. So you could say, I want to have Matplotlib but please generate the bundle for Windows, even if you're on Linux. And so it basically gets all the dependency resolution done for Windows and generate a bundle that you can now share on Windows. Yeah.
Sorry, follow-up question. If I have an environment and I pip install something into it.
That's not managed. It's an important question. We're thinking about how we could potentially either improve or whatever you call that, make it simpler to use pip packages or pip installations, connecting that with the bundle system. Right now, it's basically not part of it, but it's ignored, yes.
To be clear, though, the pip installed package works. It's part of the environment, right?
Yeah.
Right, but the dependencies are not resolved. Right. Any other questions, Fabian?
If I create an EDM bundle today, in 10 years, can I reuse it? Or do you think that...
So, good question. And so if, just like GitHub, we disappear, you don't generate just a bundle, you generate the data bundle, then you have something that contains the runtime and all the packages. You keep an installer of EDM, and then with the installer of EDM and your data bundle, if the underlying platform allows you to install EDM, you're fine. Yeah.
Which are the supported runtime versions of Python?
So which are the supported Python runtime versions? So we have 2.7, 3.4 is not officially supported. 3.5, 3.6, and 3.7 is going to come soon. One thing to know about the Python environment that Enthought supports, we're basically only supporting corporate customers. So the need to go very, very fast is very different than what we see in general. And so we typically focus on like quarterly upgrades for packages, and the runtime upgrades are basically getting slower than that. So that's basically what you have.
And the runtime support for Python 2.7 is indefinite, right?
It's going to continue for a while.
That's right.
Yeah. Depending on customers.
Okay, with that, thanks again, Didrik.
Thank you very much.
Yeah, very good.